Here's a mathematical analysis of the spirograph curve. Spirograph is a name for a toy where you put a little circle inside of a bigger circle and you roll the little circle around the inside of the bigger circle while tracing through a hole with the pen, and watch the pattern that the pen makes. Eventually the pen comes back to its starting point and a closed figure is formed. Here's an example with a different sized inner circle. You'll see in this example the inner circle has to roll more times around the outer circle before the figure closes. So the first question that has to be asked, maybe the hardest question, is why does the figure always close eventually? And can we tell just from the circumferences of the two circles how many times the inner circle has to roll around the outer circle before the figure closes? Here's a hint. The inner circle had exactly 1/2 the circumference of the outer circle. Then it would only have to roll once around the outer circle before the figure closed. If you want to figure this out on your own, you should pause the video now because I'm going to give you the answer. The reason that the figures always close is that this is not exactly a wheel, but a gear. And there are gear teeth meshing, and since there are only a certain number of different teeth on the inner circle, eventually, when it comes around to its starting position, it'll be in the original tooth position. For example, let's say we had 24 teeth in the outer circle and 13 teeth on the inner circle. And we numbered our teeth so that we could watch the tooth number of the inner circle and the outer circle as the spirograph pattern is being made. Then we see that when the teeth number gets up to 13, the inner circle resets back to 1. The outer circle continues all the way up to 24. And when the outer circle gets all the way up to 24 and goes back to 1, now we see the inner circle is 2 teeth short of its original starting orientation. And I think you can see that there are going to be 13 trips around the outer circle before the figure closes on itself. So, in other words, the number of trips is the smaller number of the reduced ratio of the circle circumferences. That is the number of times that the inner circle has to roll around the outer circle. So we're going to hold on to this fact and come back to use it later. Now let's figure out the easier part of the question. What is the x and the y coordinate of that point on the inner circle as it rolls around the outer circle? So let's say we have a starting position like this at the right, and we're going to roll the inner circle until it reaches some position over here. What happens if we try to follow the point that is originally the point of contact? Well, for simplicity, let's pretend that the outer circle is centered on the origin and that the angle through which the inner circle has rolled is called theta, measured counterclockwise from the positive x direction. Then we can characterize the orientation of the little circle after it's rolled by another angle that I will call alpha, also measured counterclockwise from the positive x-axis. Alpha and theta are not independent of each other. They are locked into a relationship from the fact that the circle is rolling without slipping. In other words, if I look at the arc length of every point on the inner circle that has been in contact with the outer circle, that must be equal to the arc length of every point on the outer circle that has been in contact with the inner circle. Those two arc lengths must be the same. Now let's name the radii. Let's say the radius of the larger circle is capital R and the radius of the smaller circle is little r. Then it's fairly easy to determine the value of this arc length. It's capital R times theta, which is just found from the definition of the radian. Since those two arc lengths are the same, we can now deduce this blue angle on the inner circle. That angle must be equal to capital R over little r times theta. And if you're not sure why that angle has to be r over r times theta, compute the arc length of the inner circle by multiplying that angle by little r, and you'll see that the arc length has to come out to the correct value. Now that this blue angle is identified, I can see that by adding alpha plus that blue angle, I go more than once around the circle. I go once around the circle plus theta. So I have this equation. R over r times theta plus alpha minus that extra theta is equal to tau, one trip around the circle. And from this relationship I can solve for alpha. Now I'm going to use a little trick. I'm now going to modify alpha just by subtracting off tau. You can always subtract tau off an angle and you get a coterminal angle. So it'll make no difference. Now that I've figured out what alpha is in terms of theta, it's very easy to write the position of the pen. Okay, first of all, we know the position of the center of the circle. It's got to be x equals r minus r cosine theta, y equals r minus r sine theta, because that center point, the center point of the little circle, is just going around the origin in a circle with radius capital R minus little r. So all I have to do to find the x and the y coordinate of the actual orange point is consider another circle of radius little r and something going around at an angle theta. So I simply add the x coordinates, so x equals r minus r cosine theta plus little r cosine alpha, and then add the y coordinates in the same way. And I now have an expression for the x and y coordinates of this orange point, and if I graphed that, I would see the correct curve. So I'm going to substitute in now alpha in terms of theta so that I could write this whole thing in terms of a single parameter. And I get x equals r minus r cosine theta plus r cosine of... Now you may notice something a little strange here. Did I really put in the expression for alpha? Not exactly. I left off this minus sign. Why did I do that? Because cosine is an even function, so the minus sign doesn't matter. I'm just writing it in a simpler way. And then the y would be r minus r sine theta minus, hold on a second, why did I put a minus over there when there's a plus over there? Again, the answer is I'm just writing it in a simpler way. The sine function is odd. So instead of the sine of negative alpha, I'm writing negative sine of alpha. And that's the simple way to write the x and the y position of the orange point in terms of the parameter theta. But we're going to improve these equations. If we want to graph this on our graphing utility, then we don't want to have to set the window parameters every time we regraph them. So let's make the capital R a constant. For every spirograph pattern that we draw, we'll make capital R equal to 1. Furthermore, the ratio of capital R to little r has to be a rational number. So let's, instead of calling the ratio R over R, let's call it M over N, where M and N are relatively prime integers. So instead of picking the radii, we're going to pick the number M and the number N. And that way we know we're going around the outer circle exactly N times. And since that means theta is going between 0 and 2n pi, why don't we define our parameter t as theta over n? That way t will always go between 0 and 2 pi, no matter what values of m and n we have. So substituting these three equations into our parametric equations, we get something that we could type into the calculator. And when you type that into the calculator, use actual letters n and m, and then assign values to them. And you can experiment with different values to get different patterns. There's just one thing we've left out though. In the actual spirograph pattern, the pen is not over here at the very edge of the inner circle. It's actually somewhere over here, somewhere between this point and this point. So we're going to make up a new parameter I'll call f that tells me what fraction of the way out from the center of the little circle the pen is sitting. So I'm going to move the second term over to the right, and I'm going to insert a factor of f. So this is the final set of parametric equations that you want to try graphing on your graphing utility. Again, type this into your calculator and use m, n, and f. Assign values to those in the home screen and see what different spirograph patterns you could make. If you want to reproduce the spirograph pattern you saw at the beginning, that was made with an outer gear that had 96 teeth and an inner gear that had 52 teeth. You have to find the reduced ratio of 96 and 52, which is 24 to 13. And that means you have to set m equal to 24 and n equal to 13. And what do you think you have to set f to? Experiment and find out. Have fun!